Testing. Ainesh, I can see you. Can you hear me?
Can you hear me?
Yes, sounds quite clear, Ainesh.
Really?
Well, a little bit cut off, but not as bad as I would expect. Can you hear me clearly?
It's not as good an audio as it was in Singapore, but yeah, I can hear
Correct.
you.
Correct. I can hear you, and it is a bit patchy, lah, but seems like we can still communicate.
Oh no, you are cutting off.
Right. So just treat today as a trial, right? If you cannot understand, just quickly ask them, lah. Then I will know that something is wrong with the audio. Did you copy?
Yeah.
Alright. There seems to be a lag also. So I'm going to say 1, 2, 3. When you hear, you're going to say 4, 5, 6. And then I will be able to tell how big of a lag is there between us. You copy?
All right.
Okay. 1, 2, 3.
4, 5, 6.
The lag is quite normal. I mean, comparing to Singapore, it's very acceptable. Right. So let's see what happened here. So we won't try the video today. I don't think that's a wise thing to do. Anything else that you can update me about, the situation there? I mean, the connection and everything.
Well, this is about as best as it can get, I think.
It's not bad. Do you use some 4G provider?
Oh no. So pretty much what I'm doing is I have no Wi-Fi here, but I'm using data, and then I'm hotspotting from my phone onto my laptop.
That's a good idea. Usually, even in my country, same thing like everywhere. Wi-Fi is actually less reliable than data. It's weird that way.
Yeah, third world countries.
So you'll be buying data. From my experience, it doesn't cost a lot. I did that before. Okay. Right. So let's see what will happen. Let's see what will happen. Right. So you're in your room. It seems quite quiet there.
Yeah.
All right. Right. Let's try this then. Hey.
Actually, no, it's not very quiet, but it's the quietest in the house.
Okay. All right. So what do you have with you?
I have the. Okay, I don't have the stand. I can get the tablet. I have. I mean, preferably since science requires the least apparatus, I prefer to use that.
And today Kyoko is not joining, so we won't be doing much math, right?
Oh yeah, speaking of which, I missed out on the integration session yesterday, right?
You missed it? No, when you're not there, I don't do math, right? It is a little bit. It is a bit frustrating.
But I won't be for like a whole week.
Yeah, it's frustrating, but what can we do, right? Now Kyoko is sick, so you're taking turns. You're taking turns not doing it. Having said that, you at least cover the first week of differentiation and integration, no? So it's not okay. Did it cut off? Did it cut off?
Yeah, but I can hear you now.
Okay. All right. Okay. So
yeah, it did cut off, but I can hear you now.
Understood. Okay, so it is frustrating how you and Kyoko take turn to not be available, but the integration differentiation we covered is at least 1.5 weeks of lesson. So that's not bad. So worst come to worst, we'll just do it during the school days. That's the worst come to worst, right? So you're slightly prepared for it. No? The reason why I don't separate, because at this point it's very critical. We're going into the exam questions. So you're going to study the different types of questions, make you more ready. Yeah, hopefully we can do that in holiday. So, right? Okay. Now, speaking of chemistry then, all right? Speaking of chemistry, I think considering how the connection might be unstable. Let's start with the better topic lah. And let's start with chemistry lah, right? Okay. For today. Okay.
Yeah.
So you're cutting off, but are you saying that you can hear me?
Yes, I can hear you. I mean, if it cuts off.
Right. Okay. Okay. So just now something weird happened. You didn't cut off, but your voice kind of like the volume get toned down or something, so that I cannot hear you fully.
Oh, sorry. It's because I'm moving around,
Right.
Making my desk see us.
All right. Okay. So if possible, we do 1.5 hours today, right? And then we'll be doing chemistry, lah. Okay. So we won't be screen sharing also. Although I am curious, why don't we just try once? Just try for a while. You screen share your slide and let's see how bad the connection becomes. Okay, just curious. Right? Let's try that.
Okay. You can see what I'm doing.
I'm seeing something, right? Although it's a bit jaggy, but I seem to be able to follow. Now the question is, can you even access your slide? Okay. Right. What? So far it seems that I'm following you well. So let's continue. Right. Okay. Something to solve here, right? So
it's good that I downloaded.
Verify. Yeah. Okay. Right. I'm not seeing your password. Okay, good. All right. Okay, you got something. Okay, let's go back to the electrolysis, right? I was saying that we shouldn't dive into the chapter, the slide first, right? We're just talking with the Jamboard, right? So I'm happy that I'm seeing your screen sharing. Okay, let's try this for a couple of minutes. Please go to page 8. Shall we do page? I suppose. Okay, right. So let's forget about the page for a while. I'm helping you revise, okay, what we have just talked about. Okay, we're talking about...
Just give me a second, like a minute. Yeah. I need to do something so that it's less noisy from my side. Thanks. All right, we can continue.
Okay. Now, considering that this is Kolkata. Kolkata is at the south part of India, is it?
East.
East. Middle.
Yeah.
Middle.
No.
Is it?
It's in the, I'm not even in the city. I'm like in a village outside.
Is it rainy season there?
It's winter, so no, not really.
Since you're using 4G, might as well tell you lah. The moment it rains on your side, expect quality to drop until we probably cannot do vision. So when that happens, just take note. Let's see how bad it is when it rains on your side. Okay.
Highly doubt it's gonna rain because it's winter. I mean, I don't even have my fan switched on.
Oh, so winter, no rain there. That's nice.
Yeah.
Yes, that's nice. Okay, good. Yep. So that's one last thing to worry about. Now, revising you on the two things that we talk about, right? We talk about two things, two separate and related things. Do you remember what they are?
Yeah.
Yeah, tell me a bit.
So, we talked about electrolysis and battery and how they're the opposite of each other.
Right.
And how electrolysis recharging battery.
Right. Right. We talk about something more than the other. That would be.
We talked about battery.
Right. Now you tell me what you understand about battery.
Okay, so there has to be two metals connected to salt, a liquid salt, and then leading out to the output source.
And don't say output source. Don't say output source. Is whatever device needing the battery, right?
Yeah.
All right then.
So the two metals, one of them has to be less reactive than the other. In this case, it's zinc and copper. And hold on.
Is it possible for different metals, right? The metal is different, right? Is it possible for different metals to have the same reactivity? That means they are not more or less reactive than each other.
No.
All right. So when it is different, it will be, one will be reactive than the other, right?
Yeah.
Okay. So why did we? Why is the practical world choose to use zinc and copper? What's your understanding?
Because zinc is very cheap and copper, I mean, while not so cheap, it is portable and it works in different scenarios.
Don't forget to mention that they are quite further apart. Not very far, but they are quite further apart.
Yeah.
Because the further they're apart, the more voltage the battery will give you, right? Right. Until this point, we learn all things that we understand from practical life. When I say, oh, battery gives you voltage, I think you kind of understand that. Right? Yeah, battery gives me 1.5 voltage. Yeah, my power bank will output 5 volt. That's what my handphone wants and whatever, right? But so far, whatever we talk about is probably not going to be covered by the slides and probably of no interest to exam. Okay, what else do you understand about battery?
I mean, do you have to dropping down, getting up thing?
Sure. That the syllabus will care that. So what happens in a battery, I guess
Wait, where is copper in the reactivity series? Is it
below H, right? So when you draw the reactive series, group 1, 2, 3, right? Then carbon, right?
Yeah.
Carbon. Then zinc, iron, and lead, right? The three in the middle, and then hydrogen, and then the noble metal, right? The precious metal. The first precious metal is copper, copper, silver, gold.
Oh yeah, okay.
So it's kind of like below there.
I thought copper was after group 3 metals.
After the 3 metals, and below hydrogen. So yeah, okay. So it's there. Right?
Yeah.
All metals are in the reactivity series, but they just choose specific metals to talk about, right? They just cut it off, you see. So what else do you understand about the jumping up, going, whatever?
I guess so. Pretty much, the higher you are, the more you have to jump down. So the higher you are, the easier it is for you to convince someone below you to jump up.
Right. So in this case, who jumped down?
Zinc.
Becoming?
Is zinc 2+.
In the process, he does what?
Makes copper go up.
No. Okay. Before that, the reason why you learn redox, because then you can say something like this: when zinc drops into zinc 2+, making his life happy, right?
Yep.
He has to, in the process, do what? Redox. I mean, zinc becomes zinc 2+. Obviously, he has to
oxidize.
Yeah, which in the process of that, we say the important point. So when you oxidize,
you lose electrons.
Yeah, you lose electron. In this case, 2 electron, right? 2 electron. Yeah. Nice. Losing an electron cannot happen without somebody else gaining electron. That's what you learn in the.
So what's the opposite of oxidation? Reduction.
Yeah, reduction. So if somebody has oxidized, somebody reduce, somebody has to accept the electron. So in this case, you're claiming that Cu accepts the electron. Yeah, so Cu gets reduced. That would be wrong in a sense that Cu will never consent to do that. It's not wrong if he can, but he cannot. Right? So tell me why Cu cannot do that? In your own understanding or words, you need to sympathize from the Cu standpoint. How come Cu will not be reduced? He will not do that. You.
What?
Yeah. So why not? Why Cu not do that?
Doesn't Cu just not accept anything?
Yes. So why don't, in your own words, why don't Cu accept electron? Which talk about electron here. Why don't it do that? I mean, name somebody who is very willing to accept electrons. Name somebody.
Chlorine.
Yeah. From chlorine become chlorine
Because
minus.
copper is a metal, so it doesn't
Yes.
want to gain electrons.
Yes. He wants to lose electron. It's totally counter to his life goal. If you think
Yeah.
about it, you're not very sure why, yeah? But that's what you have learned about metal, and metals are very consistent that way. No metals are willing to accept electron, none whatsoever.
Yeah.
Right? They want to lose, not gain. So you must sympathize from Cu point of view. He will not accept it no matter how you shove it down his throat. What will he do? Instead, he will conduct the electron away. The electron will pass through him without affecting Cu. Hence, metal a conductor. If they accept electron, they just let it pass through. This makes sense now?
Yeah.
Right. So it's not that Cu cannot accommodate more electron, but he will never take it for himself. Yeah. So the electron will travel from zinc to Cu side and then pass through Cu. Right. He will pass through Cu. Okay. And then after he passed through Cu at the border, he will encounter what exactly?
Chlorine.
Okay, chlorine minus in this case, okay, because the salt, not chlorine, but chlorine minus.
Yeah.
Just to be clear, chlorine minus will never exist by itself. There will always be a positive. So in this case, the sodium plus. So the electron passing through Cu, nothing happened to the Cu, will meet Cl minus and sodium plus. Why do you immediately mention Cl minus?
Because it needs the extra.
Now you think carefully. Is there anything in this world that will make Cl minus accept more electron? Now it's time for you to sympathize with the Cl minus perspective. Think carefully.
I don't know.
You're not sure, or you don't know, or you have a conclusion?
I'm not sure.
All right. So again, sympathize from the Cl perspective. You're talking about Cl minus, right? Not Cl. Not Cl. Not Cl. Why not Cl? Is it because I say so, or is it because there's a special reason here? It's going to be Cl minus in the salt. It's not going to be Cl. Or it's just me randomly determining that Cl minus will be there. There will be no Cl. Is it me, or is there a special reason?
It's because I remember you saying the sodium, like sodium gets leaked from the battery or something like that.
Sodium plus, not sodium. Again, you're a chemist. You're a chemist. You're a chemist student. So be clear whether you're thinking about sodium metal or sodium plus. Which one are you referring?
Sodium plus.
Let me get my point. Let me get my pen here. So to emphasize, what stops me from simply putting Cl2 there? And what stops me from simply putting sodium there? Why must it seems to be sodium plus and Cl minus? Can I actually put Cl2 there? Okay, I'm writing something on the Jamboard, but it seems like your screen sharing freeze. But now it's no longer freezing. Now it's no longer freezing. Right? Okay, now it's okay. Now it's page 7, page 7. Now I can follow you good again. Page 7, right? Okay. Yeah, so sometimes the screen sharing lags, but it seems that your audio is fine. Right? So what stops me from putting Cl2 there and sodium metal there? What stops me from doing that?
Because they'll merge.
Before they merge, it's true that when they are alone with each other, they will immediately merge with a super explosive thing lah. But it doesn't happen because most of the time, even the air surrounding the sodium contains water lah. So sodium will react with the water vapor instead, like stopping the explosive reaction with Cl2. In this case, we are proposing to drop sodium into water. So sodium will immediately react with the water instead of waiting for Cl2 lah, which is by nature is a gas anyway. This is a solid. What stops me from dropping sodium solid there? And what stops me from bubbling Cl2 gas there? Is there anything that stops me from using those two things inside the battery? Does doing that makes the battery better? If it is, then why? Well, we should be doing that, right?
Yeah.
Right. So the answer is, let's be very clear about this. The answer is, if there's a sodium metal here, first of all, it will not work because the sodium metal is too reactive. It will react with everything else. You don't want a battery to explode. You don't want that, right? So we don't use sodium metal because it's too reactive, right? We also don't use chlorine gas because if I use chlorine gas, then we're saying that we are not using Cl- and Na+, right? We're just using Cl2 and water, correct?
Yeah.
Then it won't be conducting. No? The water won't be conducting. Therefore, this is insulated from each other. Therefore, the electron will not flow. It's not a closed circuit. Do you understand? This is physics. This is physics, huh? One more time. Why does this water conduct? Because it is salt water.
What?
Why does salt water conduct? Physics, huh? Physics, a bit of chemistry. Because salt water contains positive ion and negative ion. Why is that important? Because the electricity carrier in salt water is the positive ion and the negative ion. That's what flows inside water. Water itself is pretty much still an insulator. Even though water is dangerous, it may electrocute us, it's because the voltage is very high. Meaning to say, water requires a very high voltage to be harmful, to conduct it. Very conducting.
Hello?
Okay, so we are cut off, is it?
Oh, no, I can hear you.
So when did I cut off?
No, it was like for a second. So yeah,
right.
Pretty much it needs a higher voltage for water to work.
So because based on that, we say that water is insulated. So that brings a question. So why even inside the battery? And why have salt inside the water? I can't.
Hello. Oh, that's a mess of cutoff. I can't hear you at all. Hello.
Now I have a connection problem. That's good.
Hello.
Can you hear me? Can you hear me?
Hello.
Can you hear me now?
Yeah, I can hear you now.
Okay.
Was that you?
I'm not maybe. I'm gonna write something. Does it appear? Yeah, okay. So it appears again. So it's a patchy connection. Sometimes it works. Most of the time it does. Right? So inside this battery, why don't I just do this? Okay, why don't I just take out the salt water? Okay, no more salt water. No more salt water. I just connect them with wire. That's it. Look there. Okay, no more salt water, no more Cl2. I just connect the zinc and the copper with wire. They are conducting now. It's now a circuit, right? So now it should work. Is that a battery?
No.
Why not? Please tell me.
It's because zinc doesn't lose the electron.
Cannot lose the electron. Because
there's no chlorine to gobble it.
Yeah, nobody can accept. Very good. Very good. Nobody can accept. Right? CU won't do the job. So you are saying that one more time, you need the chlorine. So which chlorine I talk about? The chlorine gas or the chlorine minus? Which one?
Chlorine minus.
Right. So you think carefully one more time. You keep saying chlorine minus accept electron. Will he do that or not?
Yeah.
No. Understand his perspective. You need to do this. Chlorine minus comes from chlorine gas, meaning chlorine gas is unhappy, accept electron, becomes Cl minus, he is happy, correct? Chlorine minus will not accept more electron. He will not do that. You must understand his perspective. Why would he?
Oh,
Why would he? Why wouldn't he? Please tell me.
Because he's already happy.
Yeah, he's already happy, right? And plus adding electron to a negative ion is not gonna happen.
Yeah,
They reject each other. Yeah, they reject each other, correct? Negative and negative repel each other. So it's a difficult prospect anyway. Some people do make Cl2 minus under lab condition, like you're really stuffing the electron into Cl minus. Is a very difficult thing to do. And after that, he will immediately reject it back anyway. So let's be clear. Cl minus will not do the job. Will not. Okay. So what will do the job? Is there anybody that can do the job? Is there anybody?
A Cl gas?
Right. Cl gas will not do the job because Cl gas is happy to receive electron. I understand. But Cl gas has difficulty being inside water. That means he doesn't dissolve very well in water. So you have very little. It does by changing to Cl minus. By the way, just say, actually, that's how he get dissolved in water, by becoming Cl minus. Which then the point is moot. Cl minus will not do the job, the original job that we want. So Cl2 gas cannot. He's not conductive, right? That doesn't solve the problem. He cannot dissolve into water, and when he does, he becomes Cl minus. So the point is moot. He becomes Cl minus not because of the electron from zinc. There's another thing going on.
Okay.
Can you accept that I'm not shoving this down the throat? I'm telling you every reason why Cl2 is not doing the job, Cl minus is not doing the job. I'm explaining. I'm trying to explain. Right? So who can do the job? Because battery works. Battery works. So who will do the reduced job? There is a candidate, okay? I need you to find the candidate. It's there. Don't you see any other candidate to accept the electron so that the battery will work? Nobody?
Oh, this is the output source? That doesn't make any sense.
Okay. What do I have here?
Plus.
Plus. In this case, it means the positive ion. Okay. The positive ion, will it do the job of accepting the electron? Will it do the job?
Sorry, I think you cut off. Can you repeat what you just said?
Of course. The positive ion, will it do the job or not?
With the Na?
In this case, the random example was NaCl because that's the salt that we know. So will Na plus do the job or not?
No.
Why not?
Because it needs to lose electrons.
What do you mean by Na plus needs to lose electron? Again, be very careful. What do you mean by that? Do you mean that he's not happy and he wants to be Na2 plus?
Wait, why would he want to be Na2 plus?
My question to you.
No,
you're saying that
sorry.
Na plus. You're saying that Na plus wants to lose electron. Are you sure about that? Are you sure about that? Okay. So one more time, will Na plus do the job of accepting the electron or not?
Yeah.
The answer is actually no. The answer is actually no. So the answer is depends. So if it is Na plus, our random example, the answer is no. The reason is very simple. You're asking Na plus to jump up. Right? Na plus is down there, correct or not? Reactivity series. You're asking him to jump up if he is to accept electron. He has to go from a state of happiness, bliss, right, into a state of, very unhappiness. The jump is higher than the drop of zinc. Same issue all over again. It's the same thing all over.
Okay, so then I think
we must replace the positive ion with something else. You must. Please replace.
Iron.
All right. Fe is just below zinc, so Fe will work. Fe will work. Fe will do the job. Fe2 plus will do the job. Even though it is a job that he does not like, he will do it. Can?
Yeah.
Can? So who is the battery in the end? Who is the battery? The battery is zinc and Fe2 plus, not copper. Not copper. Copper is there to just ensure that zinc is going to react because we want zinc to be consumed. The copper is never there to be reacted. So far, so good? Ken? The real battery is zinc and Fe2 plus. Right. Now, there are better candidates than Fe2 plus. What are they? Can you hear me? Can you hear me? Ainesh? Okay, Ainesh. Are you cut off? Can you hear me? Ainesh, can you hear me?
Hello? Hello?
Okay, can you hear me?
Yeah.
Okay.
I have no idea.
Yeah, I think it was cut off. I think it was cut off. I was asking you, is there a better candidate than Fe2 plus?
Probably lead, but
Good.
that's poisonous.
Yeah.
However,
historically, correct, lead-2 plus was used in battery. It was. It was because lead was cheap and lead was a good candidate. However, it is poisonous. So we phase it out. Are there even better candidates than Pb2 plus?
Molten gold.
The molten gold doesn't do the job. Gold will not accept electron. Hello.
Oh, sorry.
Now, you're saying Fe2 plus, right? So good. Pb2 plus, even better, but poisonous. Go down slowly. Go down slowly. What do you have?
Hydrogen.
Hydrogen plus. Not hydrogen. Hydrogen plus, which is called acid, man. Right? Which is used in battery. The old-time battery, quite powerful, used in our car, old cars are called lead acid battery. How come I'm not surprised that there is acid, that there's H plus? Because H plus does the job of accepting electron. And the zinc was not zinc, it was lead, even cheaper. Lead was even cheaper. They just straight away use Pb, the poisonous metal, and acid, doesn't care what acid, because it works.
So that means old batteries are more effective than the current ones.
No. They're not. Pb and H, very little difference, but they are so cheap. They are so cheap, and you don't care about the weight in the car. It's a car, you don't care about the weight of the battery you put in. So they're quite heavy also. They're bulky, they're poisonous, they're dangerous. But if you put enough, then you get a powerful battery anyway.
Yeah, that's true.
And then you can recharge it just like that. That's the easiest rechargeable battery ever. Just put a lead and put acid. You can recharge it almost immediately after it is gone. It's so convenient to use in the car. But you have to know how to handle it.
I forgot how recharging works, actually.
Oh, very simple. How do we charge your phone? By, plugging it in the electricity, right?
Yeah.
So how do we charge an old-time lead acid battery? By simply plugging it, the reverse reaction will happen. That's it. So again, when it is functioning as a battery, the lead will jump down, the H plus will jump up, correct? Correct.
Okay.
And then when you plug in, to recharge, H will jump down, lead 2 plus will jump up. That's all. That's all there is to it in a lead acid battery.
Lead.
In a lead acid, I'm using lead acid because it's a practical example. They don't really use it too much. Okay.
But how does it jump up? You have to force it to jump up.
Precisely. Who is forcing it? An outside source of electricity. That's why you call it electrolysis. You need electricity input to force it to jump up. Input electrical energy, output chemical energy, the jumping up of lead.
I see.
I hope this makes sense. I'm trying to make it make sense.
Yeah.
You are correct. You are forcing it to happen. It will not happen naturally. Absolutely correct. In electrolysis, all the things that we say cannot happen, because, jump up higher than jump down, correct, right? We say cannot happen. In electrolysis, that's what happened. That's the point of electrolysis, no? To force it to happen. Do you understand what I'm saying? If you don't have to force it to happen, if it happens naturally, then why do you need electrolysis? Do you understand what I'm saying?
Yeah, okay. So pretty much what you're saying is I use electricity to make force zinc to lose the ions that it gained.
Zinc 2 plus. Zinc 2
Yeah,
plus.
zinc 2 plus to lose the ions that it gained.
No, to accept the electron, the zinc 2 plus will jump up.
Oh, okay.
Go back.
Gain back
Zinc 2
its
plus go
electrons.
back. Yeah. I'm forcing zinc 2 plus to accept electron, which is of course
Okay.
not what he naturally wants, right? Not what he naturally wants. You will jump up, somebody else will jump down. The jump down will be smaller than the jump up. Normally, it doesn't happen. Okay, I get it. That's the whole point of electrolysis, because you have extra source, extra energy source input. Right? That's why. So whatever you discuss in electrolysis will always be like, no, you're forcing something that is not natural, not right? For good reasons, hopefully, you don't just waste energy for that. Right? Okay.
Yeah.
In the case of recharging a battery, the obvious reason is because I want to reuse the battery. That's the obvious reason. Right? Okay. Now back to battery load. So zinc, you pair it with Pb2 plus, okay, poisonous. You pair it with H plus. Yeah, that will work. Except that acid is very corrosive. Except there's that problem. And lead is anti-corrosive. So a lead acid battery is ironically very, very not leaky. Because lead is very resistant to acid. So you can use it that way. You can use it.
So why don't we just use it if it's not leaky?
Because first of all, it's super heavy. Lead is 4 times heavier than iron. If you think steel is heavy, wait until you leave lead. Look, just wait. First of all, that's that. Look, it's very heavy. Secondly, it's poisonous, so not a lot of people should handle it, right? Thirdly, you need a lot to make it powerful, which just makes it even more bulkier and heavier. So only suitable for a car. It's called a car battery for a reason. And even that old car battery, I'm not talking about the Tesla battery. Tesla battery is super advanced. Okay. Can you hear me? Are we cut off again? Can you hear me? Can you hear me? Ines, can you hear me? Ines, can you hear me?
Hello.
And can you hear me?
Uh,
Yeah. So let's stop the screen sharing. Let's stop the screen sharing. Okay. When was I cut off?
I remember I gave you the summary, and then after that.
Right. Okay. So if it cuts off frequently, because it have been cutting off frequently, right? So if it cuts off frequently, in the next 1 or 2 minutes, then we'll not use the audio, we'll not use the Zoom at all. We'll just use WhatsApp call and then the Jamboard. WhatsApp call surprisingly is better. Make sense? So we'll just follow Zoom totally. Okay.
Okay,
Okay.
sure.
Yeah. Okay. So let's see what happened now, because I already cut off the screen sharing. Hopefully that.
Yeah, I cut off.
Right. So zinc and H plus. Okay. In the battery, zinc will jump down, H plus will jump up. All right.
Yes. Yes.
Fe2 plus will jump up, Fe2 plus will jump up. Let me just check with your mindset. Is the jump up more or less than the jump down in a battery?
Yeah.
No, that's a question. It's a question. The jump up is more or less than the jump down in a battery.
Battery electrolysis, battery.
Yeah, so the jump up is higher or lower than the jump down?
The jump down is bigger than the jump up.
Good. That makes sense in the battery, all right? Because battery's job is to produce electricity, so you have to have it. Okay, so far so good. That's how you consume the chemical energy, no? Jump down, bigger than jump up. Okay, so far so good. Now let's go down. There are better candidates than H plus. Okay, go down.
So now you have copper.
Yeah, don't say copper. Say copper 2 plus. Get
Okay,
into the habit. You want copper 2 plus. If you have copper, it won't jump up. It cannot jump up. But copper 2 can. So more accurately, the current battery, the kind of safe battery for for us to handle is zinc copper 2 plus battery, not zinc copper. They will say it as zinc copper battery. It's actually zinc copper 2 plus battery, more precisely. So far so good.
Yeah.
You don't go to Ag plus, you don't go to Au2 plus because those ions are expensive. Okay, just say, right? Okay. So that basically sums up what a battery is. No matter what the variation, some guy will jump up, jump down, some guy will jump up, and the jump down will be bigger than the jump up. In no matter what shape and form, that is what happened in a battery. In the end, a battery question is how you will identify those two things first. Then everything else you can answer. In the end, it is just simple redox. In the end, it is just reactivity series. Do you understand me so far?
Yeah.
So in the end, electrolysis is just the reverse of a battery. No matter what I draw, no matter what we discuss from now on, our goal is to identify in electrolysis who jump up, who jump down. That's all. Understand me?
Yeah.
Now, I'm going to go to your slide. You're going to do your slide. Don't screen share it, right? So you have shared with me, right? So I go to my Google Drive. Right?
Yeah, I can send it to you again if you want.
If you can, just make it faster. Okay, so we're going to look at the slides together, you at your side, mine and my side, and then we're going to now start understanding electrolysis from your slide.
Okay, let me send it to you WhatsApp.
Okay. When the connection is worse and worse, we rely on WhatsApp more and more. That's how reliable WhatsApp is.
Yeah, that's true. Okay, sending it.
Okay, so let's open it together. I'm gonna skip slide 2, slide 3, slide 4, slide 5. I'm gonna ignore slide 5, even slide 5, slide 6, slide 7, ignore slide 8. Even slide 8, yeah, it seems very important, right? What's the title of slide 8?
Slide 8 is Introducing electrolysis. How does
No.
electrolysis work?
Yeah. How does electrolysis work? Seems like a very important thing to understand. Even then, I'm going to skip that for now. Skip slide 9, skip slide 10, skip. Good. Now, I'm at 15.2. I want to stop at the drawing. There you go. Okay, let's stop at the drawing. 15.2, slide 17. Okay?
Where I am as well. Yeah, that's where I am.
Right.
Hello.
So I need you to copy paste the slide 17 into the Jamboard, and then we go to the Jamboard. Okay.
Okay.
Right. So I'm waiting at page 8, I suppose that's okay.
Okay, please.
Right. Okay, so let's see how long until it appears in my Jamboard. Okay, starting to appear. Okay, it appears now. So quite fast, right? Right. Okay, let's see how reliable that will be. So I just move it and make it slightly bigger. Now I'm gonna use the laser pointer and I'm gonna write things in the Jamboard lah. So in this case, you cannot write, then you type. Look. So up to you, you want to use the tablet or not. Okay. Right. Now I'm gonna erase my drawing. My drawing is there for one thing only, to explain what the carbon anode is doing there. So whatever anode and cathode is, you're going to forget it for a while. My question is, how come carbon is there? I explained to you immediately. Carbon is there for some strange reason. The carbon here will be unreactive. Okay, so because carbon is not the right thing here, it's called graphite. Graphite, surprisingly, is a very unreactive carbon. Very unreactive carbon. According to the reactivity series, carbon is rather high, correct?
Yeah.
So carbon by right, when we see that, carbon is reactive, what? Correct. In the form of coal. In the form of coal. In the form of graphite and diamond, it is very unreactive. There's a structural barrier that prevents it from being reactive. So you shouldn't say carbon anode. We should say graphite anode and graphite cathode. So they are unreactive. So far, so good?
What's anode and cathode?
A very good question. I'm going to put a question mark. I promise I will explain. I promise you. It is important to know, but it's not that big of a deal for now. Okay?
All right.
Yeah. So graphite and graphite. Now, even though graphite is unreactive, from secondary 3, you learn that graphite is conducting. Correct?
Yeah.
Why is that important? That's basically why we select graphite, because it won't react. It won't mess things up, basically, but it is conducting. Why is that important in electrolysis?
Unless the circuit won't work.
Yeah. If not, then the electricity will not flow. That's what you're saying, right? So therefore, no electrolysis. Right? So far, so good. So clear, yeah? You clear why we choose graphite? Look, what are the 2 reasons that we choose graphite?
It's not reactive, and it can conduct electricity.
Yeah. So done. Those are the 2 simple reasons. Right? I hope you don't memorize this. I hope you make it make sense. Right? So we don't have to worry about graphite in the reaction. Why
you
is there?
Diamond as well.
You can use what? Sorry.
Diamond.
Diamond is, however, not conducting. So that is a big issue.
Oh, okay.
Right. You can use platinum. Look. So that means in your exam, sometimes you see platinum. Look. Why do we choose platinum? What are the 2 reasons? What are the 2 reasons that we choose platinum?
There are no reasons. As in, what are the 2 reasons?
Exactly the same reason. It is conducting and it is unreactive.
But it's expensive.
Precisely. So graphite has 3 reasons. It is cheap, conducting, and unreactive. So now you see why graphite is everybody's favorite. Right. So, but in case they use platinum, they're just their fancy way of saying, same thing like conducting and unreactive. Right? Okay?
Yeah.
But of course, we don't do that. Right? So why don't we use copper?
Cause copper is reactive.
Kind of reactive. That definitely conducting. Why don't we use iron? Iron, I mean.
Cause it's not cheap.
No, it's
No,
quite cheap.
sorry,
Irons are cheap. Irons are cheap.
iron
It
is
is cheap.
cheap.
Yeah, cheap, very cheap. Like your spoon, metal spoon is probably made out of stainless steel, right?
Yeah,
How cheap is a spoon? Quite cheap, right? Quite cheap.
yeah.
So why don't we use steel? Iron, why?
Cause it's reactive.
Kind of reactive. Good. Why don't we use gold?
Cause it's not cheap.
Yeah, it's not cheap, but it is unreactive and conducting. So you get all the point. Can you? Yeah. So back to graphite. Look, our best candidate so far. Graphite is not reacting. You see a battery here is no longer surprising you. Can?
Yeah.
So the only thing that is reacting in the end, this is chemistry. In the end, electrolysis will involve reaction. Your job is to tell the examiner what the reaction is. Right? 75% chance they will not tell you. You have to identify.
What's the reaction?
Yeah, that's our first foremost job. What is the reaction? How do I summarize to you? I summarize to you as who jump up and who jump down. Simple.
Yeah, but I can't write that in paper.
No, of course not. But your understanding first lah.
Yeah.
Remember, Ines, you're good at words. Once you understand, the words will flow. Don't worry. Don't worry about what to write. Worry about what to think.
Yeah.
I propose to you, think about who is jumping up and jumping down. I summarize to you, battery is jump down bigger than jump up, correct? I propose to you, electrolysis jump up bigger than jump down, correct? Simple, right?
Yeah.
Okay, so the only thing that could jump up or jump down in this case is there is only one thing, okay? It's not the graphite. It's not the copper wire because the copper wire is not inside here, right? So copper wire will not react also. Graphite will not react also. Will the battery react?
No.
Will this fire react?
No.
Will this container react? Presumably not, like, yeah. Presumably the container is also, unreactive, like made of glass or something like that. Like just presume that. So what could be reacting? What's our candidate?
Carbon.
Carbon will not react. We choose carbon graphite for that reason. It is unreactive form of carbon.
I mean NaCl.
Okay. Molten NaCl.
Yeah.
Now, let's be very clear. Molten NaCl is actually what? Is it Na? Is it Cl? Is it something else?
What? It's just melted salt.
Correct. You have never seen melted salt, by the way, because melted salt happens at 800 degrees Celsius. So too high for us. Too high.
Yeah.
Right? Our fire for our, for our cooking maximum is 200 to 300. Our oven maximum is like 200, 250 degrees Celsius. 800 Celsius is not within our means most of the time. So you won't see it in your school lab also. Very dangerous anyway. So let's say we have a super lab that we can melt molten, salt, make it molten 800 degrees Celsius. My question stays the same. What is molten salt? Just NaCl? Is that what happened?
No. So pretty much it reacts with Na.
What do you mean by it reacts with Na? Who is reacting with Na? Sorry? The salt reacts with Na?
No, what? That doesn't make any sense.
Yeah, that doesn't make any sense. There is no sodium metal here, by the way. Things will explode if you put sodium metal in a 800 degrees Celsius thing. That's really bad. That's just bad. Just really bad. Let me get this clear. NaCl molten liquid is Na plus in the form of liquid and Cl minus in the form of liquid. That's what molten salt is, because salt is Na plus and Cl minus.
Yeah.
So molten means they are now free to fly around. They are now free to fly around. Tell me, Ainesh, why is this important? Why don't we just put solid NaCl? Why don't?
Cause then they won't be able to react with other things.
First thing first. Secondly, they are not even conducting.
Oh yeah, yeah.
It's pure salt,
Okay.
not salt water, This is pure
Yeah.
salt. Oh, we don't do that. Okay, you may ask a question, why don't we put salt water? Salt water doesn't need 800 degrees. It will happen immediately at, I think, 15.3. So there's a reason why they choose 15.2. They start with molten sodium chloride. There's a reason. You have to understand the reason. Okay. So one more time, why do they melt the sodium chloride? Because
So that they're separate and they can be reacted with separate.
they can react, but also they conduct. So
Yeah.
two birds, one stone. So now my question is, what is the reaction? That's
I mean,
still
I'm
the
trying to
most
look at a
important.
text of clues, but I don't understand anything with this about this.
Understand. So first thing first. First thing first. The reactivity series now has two. There is the metal reactivity series, and then there is the non-metal reactivity series. Surprise, surprise, they have both. Surprise, surprise, also, they have mirror image. I was telling you that the metal reactivity series is all the metal on top, right?
Yeah.
Correct? Plus carbon and, hydrogen, right? This is already telling you, oh, goodness me, carbon and hydrogen are non-metal. How come it is inside the metal reactivity series? Oh, that's kind of hinting you already non-metals also have reactivity series. Okay, just saying that, Ken?
Yeah.
So everything here is metal plus, correct? Metal plus. So in the non-metal, you have all the non-metals, right? Including carbon and hydrogen. And what do you have below here? Non-metal, negative. Make sense?
Yeah.
All
And the
right.
same rules
So,
apply.
I'm sorry, you're saying?
And the same rules apply.
The same rules apply. It will be mirror image of each other. Everything and the order is always well preserved. There is no jumping of order. There is no shaking of order. The order is there to stay one. It's by the creation of nature or something like that, or by nature, if that's what you believe. Right? Now, where is Na plus? There are 4 sections here now, right? So there's no longer just 2 sections. Is it section 1, section 2, section 3, section 4? I just name all the sections. So where will Na plus be?
Na plus will be section 3.
There you go. He can only jump up. Simple, right? You cannot cross jump to the non-metal, by the way. That's not happening. But he can jump up if he wants to, right? No, not sorry. He won't. I'm sorry. He don't want to. If we force him to, wrong phrase, right? Now, where is Cl minus?
Section 4.
Good. What happens when you electrocute them, basically? So what happens?
Then you force them to jump up.
Na plus will jump up very high. Cl minus will also jump up very high. This is the epitome of jumping up. There isn't even a jump down. Both are forced to jump up. In the process of both jumping up, redox happen. Tell me who is giving up electron and who is receiving the electron?
Okay, so Cl is giving up an electron.
Yeah.
Then it's Na
gonna
is
be
receiving
accept.
the electron.
Correct. I just want to make this very clear. They are not happy. Both are not happy with what transpires, correct?
Yeah.
But we are able to force them because
800 degrees and also cost battery.
Yeah, electricity, yeah, battery, right? Okay, now predict the reaction. There are 2 reactions, one reduction, one oxidation. What are the 2 reactions? Just tell me one more time. Cl minus will become
Cl
And then Na plus will become?
Na.
You are, look at that, almost correct, right? Almost correct.
Yeah.
The spirit
where's
is
Na?
correct. The spirit is correct. What you say is wrong. The spirit is correct. Look, Cl minus giving up electron, right? Cl minus jumping up to become Cl, but you're wrong. You must say become Cl2 because there is no such thing as Cl. It must be
yeah.
It must be Cl. So 2Cl minus Cl2 plus 2 electron. The spirit is correct, no?
But why are we doing this?
Sorry, I'm sorry. A very good question. I'll answer you immediately after this. Okay. Please tell me, this is not the only reaction. What's the other reaction we got without looking at the slide? The other reaction will be? I want you to write down the other reaction here. I want you to write it down here. Write down.
Na can exist by itself, right?
Yes. There's a category. There's a requirement. I'll just pretend that it is correct. I'll just pretend, right? So please write down. Please write down. You must start with. Oh, you're typing. Okay, good.
Yeah. Awesome.
Right, Na plus liquid. Now look at what you're writing. Okay. So logically you're correct. Na minus the electron. However, first of all, that's not correct to say. That's not really. It's like mathematically correct. So what is more correct to say is Na plus receive electron becoming Na. That's more correct.
Yeah.
That's a much better way of saying it, and that's also the formal way of saying it. Do you agree? Right. Once you corrected that, type enter, and then look at the previous next 2 or 3 slides and tell me whether you see this reaction or not.
I also noticed the internet connections become a lot better actually. So far, not many cut-offs.
Correct. It seems that the screen sharing is not a good idea, right? So far, right?
Maybe we can try it again later. Like not today.
Yeah. So have you finished your typing?
Oh, sorry, you want me to fix it? Okay, I'll fix it.
Yeah, fix it. Better that way. And then after you fix it, go to the next 2-3 slides to see whether this reaction appears.
Yeah, it does.
All right. So your 80% understanding electrolysis of molten ion, right? 80%. Why is it wrong?
Apparently, sodium exists as liquid in natural.
You're cutting off.
Apparently, hello.
Yes.
Apparently, sodium exists as liquid in the natural state.
That means sodium plus liquid, correct, right?
Yeah, then
plus
sodium
electron, correct,
solid.
becomes sodium liquid. Why? Because it's very hot. It's like the blast furnace iron. Why did the blast furnace iron give you liquid iron? Well, because it's very hot, 1500. I hope that makes sense. This is more like, okay, you cannot experience it, but if you think about it, it makes sense. You're not going to see this in front of you, 800 degrees. Super dangerous. Very unfortunate. But it makes sense. Okay? It is true that if you write solid, they will kind of minus 1 mark from you. That's true. So far, so good, Ken?
Yeah.
The spirit is there. The spirit is there. You're 80%. You're 80%. Right? I will settle the 20% by your class because your class seems good, so that you'll pay attention. Right? Your class will tell you what the heck is anode, what the heck is cathode, and the last thing that you need to do after the 2 reaction. You are very close. Okay?
Yeah.
Now, Your class may or may not answer the question why. So that's my promise. I will answer the question why. Okay. Why is simple. There is no other way to make sodium metal. There is no other way. If you want sodium metal, this you must do. Think about this for a while. Huh? The ingredient is not complicated, is it? What do you need?
It just needs electricity and heat.
You need battery, you need heat, you need graphite. Graphite comes from your pencil, right? Pencil, yeah. That's fine. And you need salt, which you can buy. The problem is probably heat loop. So you need a container which can withstand the heat, usually a ceramic pot.
Yeah.
And then if you plug in the electricity and you heat it up to 800 degrees, I won't tell you how, there's a way to do it. Then you will have your sodium metal and your chlorine gas. There are many ways to make chlorine gas, but there are only this one or maybe two ways to make sodium metal. Only one.
Yeah.
Why don't we make iron this way? We can make iron this way. Why don't we? How do we make iron?
We mine them.
No. Mining them is the first step. You have iron ore. What's iron ore?
I'm sorry. Are you writing anything?
I'm not writing anything. I'm jotting your memory. I'm jogging your memory. Right?
Oh.
Okay. So iron ore. Iron ore is not iron. What is it?
What
section? What section? Section 1, 2, 3. Yeah, good. Section 3, correct?
Yeah.
You want to make the iron plus 2 plus, in the 3 plus in this case, jump up into iron. That's what you want to do. So how do you do that in blast furnace? By electricity? No, right? So how do you do that?
I don't remember exactly. It'll be cool if I saw the setup, but
yeah.
Do you want the setup in the general?
Never mind the setup, because I suddenly lose interest when I see your exam. But I want a summary. How do you make the iron 3 plus jump up? By, not the setup, I want a summary. By making somebody jump down. Who?
Was it carbon?
Yes. You sacrifice carbon for the sake of iron. Correct? That's the thing. So how does that happen? Because carbon jump down bigger than iron jump up. Again, that's why it works, right? The specifics are in the reaction. I teach you, you understand. The paper is not interested. At this point, I'll just be practical. It's still making sense, correct?
Yeah.
So why don't you?
I'm more interested in the essay one.
I think so. So that's why you still have to pay attention to the school. But at this point, you should be able to understand. Okay?
Yeah.
The way I teach you is I don't give you everything. You have to respect the class. I want you to go through the class with a vigor, with a clear desire to learn. But of course, you also know that you will understand because you already covered the important things. Okay.
But by the way, I think because there was so much electrolysis at the end of your paper,
yeah,
it's logical to assume you'll be taught electrolysis in term 3.
I hope so. If not, you won't have time. I hope so. Because organic chem is even longer. I'm already itching to go into OChem. Already itching.
So much stuff in Sec 4, man. But yeah.
Correct. It's very weird why your chemistry is very slow. But I'm not complaining, whatever.
Yeah.
I guess that's why it makes sense to learn now. It makes sense. Okay. So now, back to the situation. So you know how we make iron by sacrificing carbon. That makes sense, okay? Why don't you make sodium metal by sacrificing carbon? Why don't you?
Because sodium is not as useful.
No. No. Okay. I expect more from your chemistry, right? Okay. You are right to say that sodium is less useful than steel. No, I totally agree. No, I totally agree. That's correct. That's why we don't make sodium metal. It's not very useful. To us, salt is more useful. True.
Yeah.
Why bother, right? Okay, you're correct. Why bother, right? Sodium metal is a curiosity. It's a dangerous metal, and it's soft as butter, by the way. Pretty much useless for everything. You cannot use it for battery also. Too dangerous, right? So useless, right? Useless. Okay. So I give you a theoretical question. If I want to make sodium metal, out of curiosity, why don't I sacrifice carbon for it? The answer is not because it is useless. No, there's a chemistry reason why you cannot do that. What is the reason?
Hold on. Because the jump down is bigger than the jump up.
If the jump down is bigger than the jump up, then it will work.
Sorry, I mean the other way around. The jump up is small.
Very good, very good. So carbon cannot be sacrificed to make sodium.
Yeah.
That's a very good chemistry method. So the first example of electrolysis is the making of this useless and very troublesome metal. The next example of electrolysis will immediately become more practical and more useful. That means this example 15.2 serves as a primer, as a simplest example. Okay?
Yeah.
Any other question?
No.
Right. So I'm looking at the slide. Skip 15.3. Look at 15.3. 15.3, electrolysis of aqueous solution. Suddenly, we are approaching something more complicated and hopefully useful.
Is skipping all okay?
What do you mean by skipping all?
Like, are we missing out anything?
Oh, I'm telling you the most important thing first, and then you go back. I'm not saying you skip forever. I'm not saying that don't understand anode. No. The moment you understand what electrolysis is, later on anode and cathode will make sense. Okay, right. But I'm not telling you right now. I'm not telling you. Right? They explain so many things without giving you the point first, without giving you the important point. Right? I'm not sure that's the best way to learn. Now, please look at 15.3, page 29. This is now we have a picture, and then the picture speaks 1,000 words. Okay, let's copy paste page 29 to the Jamboard. I'm waiting for you at page 9.
Copy it on page 9.
Yeah. Right. I don't say that skipping is allowed. No, of course not. But I think there's a better order. So my first task for you is compare the setup. Compare the setup of page 8 and the page 9. What's the difference? Please tell me.
The most obvious difference is that it's up down, the delivery.
Why is it up down? Because of the result. Compare the result. Then we go back to comparing the setup. What is the result of this electrolysis? Strangely speaking, is oxygen gas and hydrogen gas. So you do an upward delivery loop to collect those gases. So far, so good?
Yeah. Can you make this bigger?
Of course. Good. Now, go back to the setup. There are more differences than just the fact that we have to upward delivery gas, right? I want you to notice the one difference beside the upward delivery. There's one very particular difference.
They didn't specify the anode and cathode, and
It will be graphite if they don't specify. It will be just graphite. Okay, what else?
and the NaCl is not molten; it's dilute.
It's dilute, so there is no fire lah. All that in one package. Okay? So this is your room temperature. Okay.
Yeah.
Hear me out, yeah. Because you use NaCl aqueous, dilute in this case, dilute NaCl aqueous. That means like not so salty water, simple, right? You don't get sodium metal and chlorine gas. You don't. You get oxygen gas and hydrogen gas, which kind of sounds more useful, I suppose, and less dangerous, kind of.
Yeah.
Right. So why? That you must figure out by today. Okay, you're going to figure out how come simply by changing it to dilute NaCl aqueous, you get very different results. Okay, now
we're using different gases as well.
We don't use any gas. The oxygen gas and the hydrogen gas is our results, not using. They are results. Okay, so clear that first. Write down something like those are results, not something that we use.
Okay.
Okay, so now this should be obvious, yeah. Na plus is no longer jumping up for some reason. Cl minus is no longer jumping up for some reason. Okay, so far so good?
Yeah.
By the nature of the result, H2 is the result, then guess who jump up?
Wait, what one is reacting here?
Yeah, a very good question. You don't know what's reacting. It's very weird one. Their explanation might not make sense. So I'm asking you to work backward. If Cl2 is the result, then Cl minus must have jumped up. Simple, right? If sodium metal is the result, then sodium plus must have jumped up. Now, the result is hydrogen gas. That's so weird, but working backward, who jump up? Very easy one. Very easy to guess what. Who jump up? Come on, who jump up and make H2?
Hydrogen.
Yeah, hydrogen plus. Don't say hydrogen, hydrogen plus jumps up and become H2. Now I'm going to make a comparison. So Na plus was here, right? That was the molten one. The electricity forced it to jump up. Now this does not happen here, right? Instead, H plus was here, and then it makes a smaller jump into H2, correct? That's the mirror, right? Okay, so it is only a smaller jump. This is, I think, making some sense. So we're not doing something as hard as the original thing. Even though it's useless, it's still hard. We're making something easier, forcing H plus to jump up, so it requires less energy, kind of it. So we're doing something like this. Still, there is no explanation how come H plus is jumping up, or even where the heck does the H plus come from? That's another question, right? Do you see any H plus in the setup? Do you see it?
No.
Yeah, very weird, right? It's very weird. I'm not sure whether the slides will explain that. Maybe your teacher will explain it. I have to explain that to you. Now, let's go to the other result first. There's oxygen gas. Previously, is Cl minus jumping up. The jump is also quite high. This is not happening. Instead, something else is happening. The oxygen is jumping up. To your surprise, the jump will be even higher, right? Okay, so, but who jumps up? At this point, I'm going to tell you immediately. I'm going to just tell you what jumps up, okay? This is super weird, so that's why I'm telling you. This will become oxygen. Again, a very weird guy, OH minus, also known as the base ion, right? Jumps up even higher than Cl minus, and then it makes oxygen. The reaction is here. This is super weird. You have never seen this reaction before. This is OH minus jumping up to make O2 with a byproduct. This is super weird. I'm telling you for now. And
Okay.
okay, so why? In this aqueous solution, does Na plus exist?
No.
Oh, goodness me. Yes. What happened to your Sec 3 chemistry? Come on. It's dilute NaCl aqueous. So that means what happened to the NaCl? It dissolved, right? It dissolved, right? The salt dissolved. What happens when salt dissolves? Chemistry, come on, Sec 3 chemistry.
Okay, so the salt dissolves and
When it dissolves, it separates. Do you know this? If not, then I'll be the first to tell you. It is separating. That's how it
okay.
okay. So when it separates into what?
Uh
Na plus and Cl minus.
oh yeah, yeah.
This is chemistry, yeah. So is it because it separates, then it becomes Na plus Cl minus? Or before it separates, they are already Na plus Cl minus? Which one is the correct chemistry?
When they separate, it becomes Na plus and Cl minus.
Totally wrong. That's
Huh?
why you don't understand. That's why you keep making that mistake. That's why you have a very important knowledge gap. It's very dangerous to think like that. Just because you look at this writing, NaCl, oh, it must be NaCl, right? Totally wrong. You don't understand NaCl at all. You don't understand your Sec 3 chem. You really don't. NaCl is already Na plus and Cl minus before they separate. Because if it is Na, then it will be sodium metal. Sodium metal is very dangerous. It would have exploded.
Okay.
It wasn't Na. It was already Na plus and Cl minus. That's why when the Sec 3 asks you to draw NaCl, you didn't draw Na and Cl, you draw Na plus and Cl minus. We do need you to understand this. This is chemistry. Do you have any question?
No.
Are you sure? Are you sure that you understand that part?
I'm taking a word for it.
I will test you from time to time, okay?
Okay.
So NaCl is already Na plus Cl minus before the dissolving in water. So when it dissolves in water, it just becomes Na plus and Cl minus because it is already like that, right?
Yeah.
So the Na plus and the Cl minus is there, ready to jump up. It does not happen. Why? Competition. There are other competition. The competition is, to nobody's surprise, H plus competing with Na plus and Cl minus competing with OH minus. In the competition between H plus and Na plus lose hands down. It loses immediately. Na plus does not jump up, in other words, because H plus exists. Simple. How come in their competition, Na plus lose? Immediately, definitely, must be.
Cause it's higher up on the reactivity series.
So say in informal ways, not say informal ways. Those are very formal words. Say in an informal way that you understand.
It's a bigger jump down.
Correct. So no, it's not a jump down. It's a jump up. It's a jump up. Come on, Anish. It's a jump up.
Okay.
This loses because what?
It's a bigger jump up.
So it doesn't happen.
Yeah.
The smaller jump up happen. And it's really that simple. Just like that. And yeah?
Yeah.
Now, OH minus and Cl minus. I told you that OH minus jump up is bigger because I know. You have to accept me because I've never introduced for you the full negative reactivity. Just accept me for now, right? Just accept my understanding for now. So OH minus has a slightly bigger jump. How come it still wins? Also competition factor. Okay. The keyword is in the word dilute.
Yeah.
Because of dilute, OH minus versus Cl minus kind of lose. Why does the word dilute tell us that? What is the meaning of dilute? So, what's your favorite drink? Milo, coffee, tea?
I like Milo.
Good. So, you don't like your Milo dilute?
No, of course not. I don't like it dilute.
So, I'll make you a Milo. Right? I put 1 packet of Milo, stir it up in hot water, just nice, and then I slam 10 ice cube in that hot Milo. I think you will like it, right? It's cold ice Milo, correct?
I actually personally I don't, but it's okay for the sake of the analogy, I guess.
You like hot Milo? I'm sorry.
No. I just don't like ice in general.
Oh, you don't like cold drinks?
Yeah, like for example, when I go outside, right?
Uh-huh.
I usually, if it's possible, I try to get them to not put ice in my drink.
Me too. Now, why is that so? Tell me.
It's just a hassle, and also cause it's a scam. Because if they put in ice, then they put in less of the drink.
Correct. How would you know, right? How would you know? I mean, you drink, suddenly is everything gone. You're left with ice.
Yeah, exactly.
Correct.
It's a big waste. Yeah.
Totally. I understand you. Even worse than that scam is that if you leave your drink for too long, even worse. What happened?
Yeah, because it becomes diluted with the
Correct.
water.
By the water from the ice,
Yeah.
right? And then if you leave it for half an hour, then suddenly all the ice gone, and then your Milo becomes super dilute Milo. It's very annoying. Okay, so might as well don't have ice in the first place. I totally get it. Okay, totally
Yeah,
get it,
exactly.
right? So what does dilute mean? What does dilute mean? There are more.
They are
More what? More what than what? That's what dilute mean. More what than what?
They are less concentrated.
Correct. There are more what than what. I'm using a very weird word. In a dilute situation, something is more than something else. I'm using 2 nouns here. I need you to say a noun, a certain noun is more than a certain other noun. Please tell me, in the case of dilute Milo, what is more than the other thing?
The water is more than the
Milo. Something like that. In a concentrated Milo, we can kind of say the Milo is more than the water. It's a very informal way of saying it, right? That makes sense?
Yeah.
So this explains our competition winner.
Oh, okay.
Water is more than the NaCl because dilute. So Cl minus wins out of sheer, there's just more OH minus than Cl minus. Kind of. That's a very informal way of explaining it. It's a competition.
Yeah.
So who is the source of H plus and OH minus? Who are the source? Who is the source?
The water.
Yes. Have you accepted this is also chemistry? I'm not sure that they discuss it, but water does contain trace amount of H plus and OH minus inside water just by being water.
Mm-hmm.
So therefore, now you know why our original example does not want water. It's called molten salt for a reason. Is there water in molten salt?
Yes.
No. Why?
Why
Why? Because it's 800 degrees. The water would have, in an 800-degree thing, the water would have,
it will have evaporated.
so there's no water.
Yeah.
So there's no competition. So the result winner is very clear. No? Sodium will win and chlorine will win. Why? Because there is no competition. Once you introduce competition, Na plus lose. See, H plus wins. Once you introduce competition, OH minus wins. Cl minus lose, as if nothing happened to Cl minus. I mean, I'm betting that Cl minus is happy. He doesn't want to win, right? It's not that he's jumping up, it makes him happy. But from our perspective, Cl minus lose, OH minus wins. He jumps up. Okay?
Yeah.
This is how you need to think when you kind of guess, you're trying to figure out also what will happen in this setup. You can no longer think it's only sodium plus or Cl minus. You must think in terms of competition. Okay. Now, let's look at the next few slides and let's find the setup of concentrated NaCl. Let's go and find it. Do you see concentrated NaCl in a few other slides? Which slide would that be? Which page?
Concentrated NaCl.
Which slide?
32.
Very good. Don't scroll down. I'm going to ask you, who is the competition for Na plus?
Hydrogen and
hydrogen plus.
Oh, H plus and Cl minus.
Cl minus is not the competition for Na plus. They don't compete. Na plus compete with H plus. That's it. Positive compete with positive, at least in this case. Why doesn't Cl minus compete with Na plus? Because they're doing different job. Cl minus will lose electron, Na plus will accept electron. That's not called competition. That's called working together. Do you understand? Why is Na plus the competitor for H plus? Because they are vying for the same job. What's the job? Accepting.
Okay, I'm kind of losing track.
Yeah, accepting electron. That's their job. Remember? So they are vying for the same job. So they compete. But Na plus and Cl minus are doing different complementary jobs. So they are not competing. Okay? Now, Na plus and H plus, in this case, who wins?
H plus.
Why?
Because it's a smaller jump up.
The result is still the same, right? Concentrated, same thing, right? Now, the other competition that's happening is between
OH minus and Cl minus.
Right. Last time, when the Milo is dilute, right? When the NaCl is dilute, who wins?
OH wins.
OH minus wins because there is more water, so to speak, right? Yeah. Water is the source of it. Now it's concentrated Milo. Who wins? Make a guess.
The water wins.
All right. Not exactly true.
Concentrated is the powder wins.
The Cl minus wins. Okay.
Yeah.
The Cl minus. Because their jump is similar. So the guy which is more wins. If you can accept that, the jump is similar. In the Na plus H plus case, the jump is just too big of a gap. So no matter what, H plus wins.
Okay.
Again, in the case of OH minus and Cl minus, the jump is similar. So the one with more tends to win Cl minus. Let's check out the few slides, see whether we are correct or not. Next slide. Are you correct?
I don't understand what any of this means, but
I understand. I understand that you don't understand, but look at the reaction. Did you guess correctly?
Cl on the top.
Cl minus becomes Cl2. Look at the reaction. Cl minus becomes Cl2. Look at the reaction.
Oh, yeah. So I got it correct.
Yeah. So let me explain this fancy word. Being concentrated, Cl minus are preferentially discharged. Those are very fancy words too. Being concentrated Milo, Cl minus more than H plus, correct? HL minus more than OH minus. So he wins low preferentially, right?
Okay.
Look at the next slide. Who wins?
Cl. No,
Slide 34. No, you didn't guess any plus win. You guess H plus win because the jump gap is too high.
Yeah.
So H plus win low. The concentration doesn't matter in the case of H plus, although you must admit there are more Na plus right now. But the
how will
jump
I
is
know if like when the jump up becomes too high?
in the case of the positive ion, now I tell you from experience, there's very little competition where the jump is very equal to each other. Very little. Usually the gap in the jump is very high. You can see it from the reactivities here. Okay.
Yeah.
In the case of the negative ions, for some reason, the jump up is close to each other. So you have to take into account the quantity. That means dilute or concentrated. For now, it's like that. Okay. There is one more reason. The reason that they never mentioned. Then we'll close that. Na plus does sometimes jump up when it's too concentrated. It does. The moment it jumps up, it becomes sodium metal, correct?
Yeah.
In the middle of water, guess what happened? The thermoreactive reaction. I know we don't know sodium metal. It's a big problem. When you put sodium metal in water, what happened? It'll become sodium plus again. I just said it'll become sodium. So even though sodium metal do sometimes win, it immediately becomes sodium plus again because of water. So it'll never win in that sense. Never. It'll never win.
Oh, I see.
So it does win, but it will immediately jump down. It doesn't happen with chlorine and oxygen because they don't dissolve in water. They don't react so much in water. They will escape out. So that's the collection. By the way, the Cl2 gas collection is wrong. Yeah, Cl2 cannot be collected upward. Yeah, so there's something wrong with this drawing. I'm just saying. By the way, just say Cl2 gas is heavy, so you cannot collect upward. You must collect downward. Right? It is possible to do a vacuum collection. I don't think you learn vacuum collection. It's called a vacuum collection. So it looks like an upward collection. It's not an upward collection. It is a vacuum collection. Never mind. Never mind. It's like free. Okay, now let's stop here. This is more than 1.5 hours. So any questions over?
Actually, can we go like the last part? Maybe like give a quick run through for like the first 5-10 minutes tomorrow, because I got a bit.
Yes, we will. We will keep repeating this until I feel you're ready for the exam questions.
All right.
Right now, any other question for the chemistry so far?
No.
No homework yet because you're not ready. Now, what do you think about the connection so far today?
The last part was actually quite good.
Right. So we'll settle by not screen sharing now, right?
Yeah.
Right. We'll just use the Jamboard. The Jamboard says fine. And if tomorrow something gets worse, then I'll ask you to switch to WhatsApp call.
Okay, sure.
I'll see you tomorrow.